All right, example 1. Millicent began the journey at 6 a.m. at 50 kilometers per hour. Beauregard began to chase her at 10 a.m. at 60 kilometers per hour. What time was it when Beauregard got within 40 kilometers of Millicent? So, we got Millicent and Beauregard are right here at some place. And what happened, just so you know, sometimes we know the backstory, it helps us to understand how the problem works. Millicent and Beauregard were boyfriend and girlfriend.
Boyfriend and girlfriend.
And I should tell you this right now because it's important to the story that Millicent really likes these really big handbags. Like she's got this handbag, she kind of leans to one side as she walks, it's so heavy. All right, that's very pertinent to the story as I'm going to tell it. Anyway, but they're talking to each other. Apparently it's at 6 a.m. It's probably more like 5:59 a.m. when they're talking to each other. And Millicent asked Beauregard, "Do I look fat in this dress?" Now, if Beauregard was a smart boyfriend, he would know the correct answer immediately is no. And he did say no, but guess what he did? He hesitated. Yeah, you never hesitate. Do I look fat in this? Just no. It should just be a split decision. Boom. You don't even think of it. He hesitated. He looked at her first before he answered no. Wrong. Anyway, so she took her handbag that she always carries and she goes and hit him right in the head and he got knocked out because she was mad at him. She took off. But she's going 50 kilometers per hour, which if you don't know is about 30 miles per hour. It's not very fast. All right, she's driving her car because she felt bad immediately once she hit him in the head, but she goes, I got to get away from him. So she's going away. Maybe he'll chase me.
He's dead. So.
Right. So anyway, so Millicent's off going this direction here, and that's Millicent. And then Beauregard woke up at 10 a.m. He probably woke up at 9:59 a.m. kind of woozy. Oh, what happened? Oh yeah, I hesitated. That's what happened. So anyway, so he wakes up. He jumps into his car. And he knows that she went that way because that's the only way Millicent ever goes. She just went that way. So this Beauregard, he begins to chase her. He's going at 60 kilometers per hour, which is about 36 miles per hour, in case you're interested. Not very fast either, but faster than Millicent ever drives. She only goes 30. That's how heavy her foot is. That's the hardest she can push that gas. But so he's chasing her, and he doesn't get all the way to her. It says, what time was it when he got within 40 kilometers of Millicent? All right, so this is the end for Millicent, this is the end for Beauregard, and the difference in distances is 40 kilometers. I know 40 kilometers goes in the picture because it's a distance. Okay, when I'm looking at units, kilometers per hour is a unit of speed, hours is a unit of time, kilometers is a unit of distance. So anytime I'm drawing a picture, distances go in the picture. That's the only place 40 kilometers is going to go. So once I've used it in the picture, it's gone. It's no longer going to be considered anything important for the work of my problem. Millicent went an unknown distance. Beauregard went an unknown distance. So I'm going to put that as d sub b and d sub m. And looking at the picture, segment addition postulate, short plus short equals long. So d sub b plus 40 is equal to d sub m. Again, that's priority one in every one of these problems. Identify how the distances relate to one another. All right? If you can come up with some humorous story as to what happened in the problem too, sometimes it helps keep you on task as you're doing your boring math homework. All right, so continuing on. Once you've established how the distances relate, we've got our Millicent and Beauregard are our categories. Now we go to rate, time, and distance. Hey, how fast is Millicent going?
50.
50. Unit of speed is kilometers per hour, km per hr, which tells me time is in hours and distances in kilometers. Sometimes we establish units of things, sometimes that helps us too, so it doesn't hurt to put that above our chart like that. Beauregard, of course, is going 60 kilometers per hour, so the rate is basic. It's exactly what it is. No concerns on that. The times, on the other hand, are a little bit more difficult here. And what they've done here is they've given us starting times. 6 a.m. is Millicent's starting time. 10 a.m. is Beauregard's starting time. And typically, when we've had these starting times, we've also had an ending time, right? This question specifically says, what time was it? So we don't know the ending time. All right? So what we have to do is we have to look at the discrepancy in their times to establish what their times are, because these times are not 6 a.m. and 10 a.m., but is elapsed time of their travel. How long do they travel? So if I just say that Millicent traveled for T hours, because I don't know how long she traveled. Does anybody know how long she traveled without already having worked out the problem or looking in the book? No. So we don't know at this point for how much time she's traveled yet. So T represents her time. Beauregard left at 10 a.m. Does that make him travel more or less time than her? Less by how many hours? 4 hours less, right? So 4 hours less is t minus 4. That would be his time. I could have also made Beauregard's time t. She traveled 4 hours more, so t plus 4. And if you're not sure about the order of subtraction, that'd be the way to avoid subtraction. Make Beauregard's time t, Millicent's is t plus 4 then. All right? But either way, you do it. So at this point, t represents, when I get t equals in my equation, which I always get either t equals or r equals, right? That's what I always get. When I get t equals, that represents Millicent's time. It doesn't represent the time on the clock, what time it was. So make sure that you still are answering the question. So once I know the rates and the times either as specific numbers or as algebraic expressions using at most one variable, I then do rate times time to equal distance. So 50 times t would be 50t for Millicent's distance. T minus 4 being a binomial, I have to distribute, so 60 times t minus 4 makes 60t minus 240 for Beauregard's distance. And according to my equation, Beauregard's distance goes there, Millicent's distance goes here. So 60t minus 240, that's Beauregard's distance, plus 40 is just part of the problem, equals, and Millicent's distance is 50t. Okay, once I establish what both those distance expressions are, they simply go into the equation I've already created, the structure I've already created here. Again, plus 40 is just part of the equation structure I created. And then I simply solve this using good algebra. I'm going to move the 60t over here. Negative 240 plus 40 makes negative 200. 50t minus 60t makes negative 10t. We divide both sides by negative 10. That gets me t is equal to 20 hours. So Millicent traveled for a total of 20 hours. The question to ask, that's being asked, what time was it? So we take her beginning time, which is 6 a.m.,
You deserved it.
and we add 20 hours to that. All right, let me just ask you this. If she traveled for 24 hours, what time would it be? Maddie?
What?
All right, she traveled 24 hours, what time would it be?
Well,
If it's 6 a.m. and you go 24 hours in the future,
2 a.m.
6 a.m. again. All right, you're not answering my question though.
You said 20 hours.
Pay close attention. Let's listen to my words again. If it's 6 a.m. and she traveled for 24
Oh, that's 6
hours,
a.m.
it'd be
yeah.
6 a.m., okay? 4 hours before that, as Maddie's already said, will be 2 a.m. Now, please do this the next day. 2 a.m. the next day. Oh, I forgot to mention they're both in vehicles that don't need to be gassed up ever.
Gas up.
Yeah, they're magic
Plugged
vehicles
in.
that go on forever. They got perpetual motion engines in them that go on forever, right? So they don't go very fast, but they don't have to be filled up, so they're pretty efficient.